Hello friends, today we will talk about a novel vibration control technology developed at the Department of Earthquake Engineering, IIT Roorkee. This is a very simple passive control strategy which can be used to reduce the lateral drift and which will come in very handy for improving the seismic resilience of existing as well as new buildings, and particularly very important from the point of view that with the recent revision of IS 1893, the seismic demand has increased by several folds at several locations, and existing building stocks are vulnerable according to or deficient, seismic deficient uh, after this current revision, even if they were designed according to the earlier code. So that's the outline of today's talk. So essentially based on the concept of tune mass damper, and we will talk about tune mass damper and our implementation, uh, our take on the implementation of tune mass damper system and how do we go about it. So the context of the problem, uh, the basic requirement is improving the seismic withstand capacity of buildings, both new as well as existing buildings. This is necessitated in view of the recent version revision of IS 1893, with seismic design forces increasing by almost 100% at several instances, more than 100% in several situations. The challenge is not to compromise with the operational utility and efficiency of buildings while improving the seismic withstand capacity. For example, if we try to improve the lateral load resistance capacity by incorporation of bracings and all, so that is, first of all, it's a very messy affair, and structural frame may not be really uh, able to take on that additional load, additional structure, and that will also compromise the functional requirement, operational utility of the buildings. And then, uh, most crucially, the foundation itself may not be adequate to take up the additional load of these bracing systems. So the objective for this particular issue that we are dealing with is to devise a non-obtrusive vibration control scheme using distributed tune mass dampers for seismic response control. We describe experimental investigation to validate the design and to quantify the effectiveness of the control strategy. And then we also develop and validate analytical model which can be used to investigate the how much benefit this distributed tune mass damper can provide for the design of more complex systems. So tune mass damper in itself is a very old concept, more than 100 years old. And in recent times, the most famous example is the pendulum system at Taipei 101, the 101 storied tower at Taipei in Taiwan. And the whole idea is this auxiliary mass is suspended through cables and viscous dampers, and these cables and mass is arranged such that the natural frequency of this auxiliary mass is tuned to the natural frequency of this host structure. And the whole concept of tuned mass damper works on the principle that when the primary structure vibrates, the auxiliary system, smaller system with very flexible spring compared to the stiffness of the primary structure, uh, vibrates out of phase with the primary structure, and that provides reaction at the connection of auxiliary mass with the primary structure to oppose the motion of the primary structure, and that is how the vibration control actually takes place. So that is a basic idea behind a tune mass damper. You can read more about this particular building from this Wikipedia entry. Now, installations like Taipei 101 are very effective in controlling lateral drifts, but this kind of installation needs to be conceived of and planned at the design stage. It is not generally suitable as a retrofit solution. For example, you may like to notice that this entire damper assembly, pendulum damper assembly, occupies 3 floors of this building. 3 floors, and that's the most expensive real estate in Taiwan, Taipei. So we are losing commercial space, 3 stories of commercial space to accommodate this one pendulum. Of course, they are generating revenue by selling tickets to visitors to who want to see this pendulum, and it's a very beautiful view, no doubt. But nevertheless, commercial use of this building, these 3 floors, is still something that needs to be considered. Generally, when we design for lateral load, earthquake resistance, and lateral loads, we that process actually builds significant uh, safety margin with respect to vertical loads. So there is generally substantial safety margin available in buildings with respect to vertical loads. So that gives us this idea that maybe instead of having one huge pendulum at the top, we can distribute small spring mass oscillators across several floors of the building, and they can be accommodated and they can be tuned to same fundamental frequency, or they can be tuned to different frequencies at different floors as per requirement. And then a false flooring may cover up these small oscillators, and the entire floor space may be available for normal use. I'll describe that in next few slides. So typically, up to 10% of the seismic mass at each floor can be distributed as mass blocks supported by suitable springs. Now, if each mass block is taken as a small entity, then the required spring is also small, very relatively very soft spring, right? To get the same frequency that we are targeting, that is the natural frequency of the structure, or whatever natural frequency. So for a small mass, we also require a small spring, and which can be fabricated at site very easily. We'll see. I'll describe how this is being this is done, and this entire assembly of mass and spring can be accommodated within a depth of 120 mm, 120 millimeter, only 4 inches. So the entire, but practically entire floor height is available for use, normal use, and whenever required, these tune mass dampers will vibrate and damp out the vibration of the host structure without anybody having to worry about anything. So how does this work? So the first thing that we need to look at is these small blocks that you see here, concrete blocks. Now, if I place it on concrete to concrete interface, friction interface, coefficient of friction is very high, of the order of 0.8 or more. So practically the block will not slide. You might have experienced, I mean, concrete blocks on top of each other, they are not very easy sliding systems. Now the whole idea of tune mass damper is that auxiliary mass should vibrate easily. So how do we do that? So we need to prepare the surface. So on top of this concrete roof slab, we place these thin sheets of ultra high molecular weight polyethylene, UHMWPE. UHMWPE is a polymer which is non-toxic. In fact, it is so non-toxic that it is often used as a orthopedic implant, and it is very tenacious and very high abrasive resistance properties. And these concrete blocks are with concrete cast in these steel trays, and we let the steel tray to be there. So concrete is in this steel tray. So the purpose of this steel tray is this steel and UHMWPE interface is very interesting. The coefficient of friction between this steel and UHMWPE is very small, of the order of between 0.15 to 0.20. Right. So that makes it a very smooth interface where over which this block can slide very easily. At the same time, it provides enough friction resistance to control the vibration amplitude of these blocks as it vibrates. Right. And in order to develop the reaction of the spring, I put these reaction blocks of steel angle sections. So I prepared this slot using these angle sections. You can see this one angle section, angle section, angle section, angle section. So in between these, we paste these UHMW sheet, UHMWPE sheet, and on top of this UHMWPE sheet, we place these concrete blocks, and then these concrete blocks and in between these concrete blocks and these reaction block, we insert these leaf springs. Right. So kind of tongue-like construction that we can just fashion out of sheet metal. Sheet metal as right. Sheet metal of required thickness and tongue length of required length, and we can fabricate these leaf springs and then give heat treatment at site, and they are ready to be used as a spring material, and very effective. You don't really need any specific helical spring of specific stiffness, depending on whatever natural frequency is to be targeted. We can fabricate these leaf springs accordingly of desired stiffness, and they can be inserted. Now, in this case, I used these steel angles to make these slots to house these blocks. It is quite possible to make this roof slab as a inverted waffle slab, and that will have these slots available ready-made, where this surface can be prepared and these blocks can mass blocks can go in with springs inserted in between. So this and the whole idea is this single mass block can work as a damper, or the auxiliary mass work in both the direction. We can place springs here also, we can place springs here also. So one mass block effectively takes care of both the horizontal directions, vibration in both the horizontal directions without any problem. So that's the test frame with dampers on top of this prepared surface. And so a small concrete block about 32 kg each, including the steel casing, is placed on the roof with ultra-molecular, high molecular weight polyethylene UHMWPE interface for controlling friction. These mass blocks are supported against steel anchor blocks by suitable leaf springs of required stiffness for the desired tuning. The coefficient of friction for steel and UHMWPE interface is between 0.15 to 0.20, which provides sufficient smoothness to ensure vibration of auxiliary masses. And this test specimen is subjected to IS 1893 2026 MC level ground motion for zone 5 on the check table. And these are the test results. So first, free vibration. As you can see, the frame has a natural frequency of 7 Hertz. It completes 7 cycles of vibration within 1 second. And this is the typical geometry of that leaf spring that we fashioned. So essentially just sheet metal cut and bent into this kind of shape, tongue shape, and then given heat treatment, quenching, oil quenching to generate the elasticity that can develop the reaction at the anchor reaction blocks. So length and this opening can be can be calculated as per requirement. Right? So if we have more longer these tongue lengths of this tongue, it will be a more flexible spring. If we reduce this length, it will be a more stiffer spring. And similarly with the thickness, if I reduce the thickness of this sheet plate, it will be a flexible spring. If I increase the thickness of the sheet, it will lead to give a stiffer spring. So this is the excitation horizontal component, horizontal acceleration. Vertical component is about approximately 2/3 of this time history. This is recorded, what we recorded on the table. You can see the accelerometer here at the bottom that records the table motion, and the accelerometer at the top records the response of the roof. So this is done for both with and without damper testing. So this is the response recorded at the roof without damper, and this is the response at the roof when damper is installed. So you can see the response reduction. The scale is kept uniform for all the three time histories so that you can the difference is visually appealing. So response reduction you can see in this case. So from about approximately 15 meter per second squared, it is reduced to about 10 meter per second squared peak roof acceleration. And here also accordingly. So we can have more quantitative result. This is the response of flow and floor spectra. So this is horizontal component of ground motion, spectrum compatible motion. That is the spectrum of that motion, response spectrum of that motion, 5% damped. And these are the spectra of the time history recorded at the roof. So floor spectra. So this dotted, this one is for without damper, and this one, lower middle one, is the floor spectra of roof motion with damper installed. And then we can also compute the transfer function between these two output and this input, and this output and this input. So that transfer function is here. So you can see that without damper, it's a very sharp peaked transfer function without damper, and with damper, it is much more well contained transfer function. So response amplification, if I quantify, it is reduced by 30% for a tuning ratio of 0.6. We could achieve tuning ratio of 0.6 because it did not go into several trials with this leaf spring. Whatever leaf spring I got in the first trial, we ran the experiment with that, and that gave us tuning ratio of 0.6. So even for a tuning ratio of 0.6, the response amplification is reduced by 30%. You can see the video of the test from this link. It's an active link, and you can have a look at it. I'll run the test here for you. Just a minute. So I'll play this record. And you can see this mass blocks, auxiliary mass blocks vibrating, and these springs, reaction of these springs actually helps in arresting the vibration of this primary structure. And you can see that this is a very small, very small depth is required to accommodate this. And this entire thing can be covered by false flooring and the entire floor can be used uh, normal as a normal case without any problem. So continuing from that, we developed the analytical model for uh, use with more complex structures. So analytical model, I mean, the frame is simple single degree of freedom system. So mass and stiffness and damping we computed from logarithmic decrement of this free vibration. So that is about 0.9%, and natural frequency is of course 7 hertz, and the mass and stiffness accordingly we calculated mass according to the dimension of the roof slab, and on top of it we have these four uh, auxiliary masses supported by the spring and this friction interface. And now because of this friction interface, this system becomes non-linear particularly, and this entire thing has to be solved using non-linear dynamic analysis by using Ragakatta fourth order scheme. Of course, we can work out equivalent viscous damper for this also, because the damping is anyway going to be very, very small, and the entire thing can be analyzed using linear analysis as well. So now we have analytical model prediction. This is what the response of this mass is predicted for the uh, this base excitation that was recorded. So this is the response predicted by the model, and this was the response of the roof that was recorded by the accelerometer. As you can see, the agreement between the two sets of results is very, very good. And just to explain, just to show how good this predictive capability of this model is, we blow up the response between for 5 second window between 7 second to 12 second, that will capture this particular peak response. So this is what we have. So continuous curve is the analytical result, and dotted curve is what we recorded from the experimental uh, investigation. And as you can see, the result is agreement is very excellent, and naturally not much happening here. It's a single degree freedom system, so we are only trying to model slight modification, perturbation of single degree freedom system result by these small oscillator masses. So not much deviation uh, from the between analytical and predicted experimental and analytical results. So response reduction is by 30% for tuning ratio of 0.6 with mass ratio of about 7.7%. So the four blocks of 32 kilo each, they add up to about 7.7% of the total uh, roof slab mass. And if we increase in the analytical model, if we improve the tuning ratio to 0.9, the response gets reduced by 40% for the same mass ratio. If we increase the mass ratio to 10%, this will also increase the further, there will be further reduction in the lateral drift or the vibration of the primary mass. So now, having done with the single degree freedom system, we now look at the possibility of what happens if we distribute these masses across several heights. And we took a simple four-storied shear building model, and each floor housing these four oscillators. So essentially, we are looking at a system where we extend this particular system by vertically. So just replicate this three more times. So this becomes first floor. We can have second floor. We can have third floor. We can have fourth floor. Exactly identical. So that is the kind of system we are looking at. So analytically, this looks like first floor, then four auxiliary masses on top of first floor, and then first floor supports this second floor, and second floor also supports these four auxiliary masses, and so on. Third floor with four auxiliary masses, fourth floor with four auxiliary masses. And again, this model is analyzed with for the same excitation, same set of excitation, ground excitation, and the response with and without these auxiliary masses is computed, and this is what you see here. So continuous curve here is the result with damper, and dotted curve here is the result without damper. So for same 7.7% tuning mass, tuning ratio, the mass ratio, 7.7% mass ratio, and for 0.9 tuning ratio, this is the response reduction that you can see, substantial response reduction in the story drift at the first floor, right? When you have damper and when the damper is not there. And similarly, for the, I mean, this is what you observe at all floors. So I just present the results for fourth floor, top floor. So story drift, total deformation is reduced considerably with damper. And when I take the interstory drift, so that is the difference between the deformation at third floor and deformation at fourth floor, again you will find that the interstory drift is greatly reduced. Now this interstory drift is what is that is what proportional to the forces developing in the columns. So that addresses the major concern of seismic withstand capacity. So for this analytical investigation, we found that response reduction by 60% for tuning of 0.9, tuning ratio of 0.9, and for mass ratio of 7.7, the same 32 kilogram, four masses for the same, so the same mass ratio. And this provides a very practical means for controlling story drifts. And this is also very helpful in protecting the buildings on hill slope, where we have this nasty problem of short columns on for uh, buildings on hill slope. So we have floors resting on stiff short columns on the hillside and flexible columns on the roadside. And when you have this monolithic roof slab or floor cast with columns tied together, in case of drift in during earthquake, the short column attracts huge uh, shear force, and that causes the main primary cause of damage to the buildings on hill slope. So if we can arrest the drift by using this kind of mechanism, that protects the short column, and they can be designed much more conveniently and much more efficiently. And this particular technology has been granted, and in India Institute has received this patent from India, intellectual property controller of intellectual property of India. Indian patent is granted, and this result is also published in Soil Dynamics and Earthquake Engineering, volume 181, 2024, last year. So I hope you find this uh, concept useful, and uh, particularly from the point of view of addressing the seismic deficiencies and uh, the need to address large increase in seismic demand with this recent revision of IS 1893. Please feel free to uh, seek details about this technology regarding implementation, how to go about it, and comments and suggestions. Thank you.